Hi, my name is Alex Wang, and today I'll be presenting my project, Computational Assessment of Macrocyclic Host-Guest Ion-Dipole Interactions with Negative Pores. But what are macrocycles? Well, they're compounds with large central rings forming cavities. Some of their key properties include having simple organic backbones, spontaneous self-assembly, which is where adjacent macrocycles will bond with one another to form specific arrangements, and finally, molecular recognition, where a macrocycle will bind to a specific gas based on the size of its cavity. This is comparable to enzymes that only bind to specific substrates. They're useful in host gas chemistry, which analyzes non-covalent interactions between a larger host compound such as a macrocycle and a smaller guest compound. Some potential applications for macrocycles include combating ion imbalances, which occurs in cystic fibrosis, Alzheimer's, myotonia, and channelopathies, gene delivery, bioinspired catalysis, biochemical sensing, and drug encapsulation and release. Some prior work in macrocyclic host gas chemistry include Lee's 2013 cyanostar compound, Wang's 2020 MPE macrocycle, and Mao's 2020 DPA macrocycle. However, one key issue with all these macrocycles is that they lacked a very strongly charged pore because their cavity or innermost atoms were mostly hydrogens. Therefore, to approach this issue, my macrocycle was a 6-mer oligoamide, which acted as a highly polarized host. The geometric structure is presented in media file 1. The advantages of this oligoamide macrocycle are its rigidity afforded by intramolecular hydrogen bonding and pi stacking interactions leading to self-assembly. It also has 2 enantiomeric forms, either M or P. Finally, the remote steric effect or folding of the precursor polyamides was beneficial for greater selectivity for the 6-mer during synthesis. Next, the purpose of the guest selection was to model the macrocycle's host-guest interactions. So I selected a guest of a Dapko derivative shown in figure 9 because of its relatively high positive charge density and cheap and accessible nature for future empirical testing. Notice in media 2 that there is a bulky equatorial region to fit the macrocycle. In order to computationally assess the macrocycle's host-guest properties, first the molecules were built inside Avogadro's software. Then the guest was placed inside of the host. Next, geometric optimizations that followed the Born-Oppenheimer approximation occurred, where I used a Gaussian and Amsterdam density functional. I also explored an energy decompositional analysis. Finally, a Spartan software package was then used in order to generate the electrostatic potential maps. Energies of interactions were calculated by subtracting the energies of the system together by the energies of each individual part. Here are some example geometrically optimized final structures of the host-guest systems. Notice that the ratio of the host and the guest is not necessarily 1-to-1, as there's an example of a 2-host, 1-guest system. Also, the vertical placement of the guest inside the center of the outside macrocycle. I first analyzed conformation, which is the 3D configuration of the macrocycle. The 2 existing conformations with the bowl and the chair, shown in figure 14A and B, respectively. The 2 competing factors that resulted in these conformations were repulsion of inner oxygens and ring conjugation. The bowl conformation had a smaller homo-LUMO gap, as can be concluded in table 1, and therefore was a more conjugated system with greater delocalization of charge. The chair, on the other hand, had a distorted structure with less oxygen repulsion, which corresponded to lower coulombic and potential energy, demonstrated in table 2. Next, I analyzed pi-pi stacking interactions where self-assembly occurred and the type of overlap that existed. The 2 different forms appeared and either had the pi orbitals indicated by the purple aromatic rings directly on top of one another, like in part A of figure 15, or angled and displaced, like in part B of figure 15. Pi stacking interactions were far more stable when they were parallel displaced, in order to minimize destructive overlap, demonstrated in figure 16, or corresponding to B of figure 15. This was confirmed by dimerization energies in table 3. Charge distribution was measured by Spartan calculated electrostatic potential maps, with blue representing electron deficiency while red represented the opposite, or electron richness. In figure 17, the top image is the host while the bottom is the guest. The binding of the guest structure with the host is based on charge transfer, as the negatively charged oxygen atoms in red on the top of figure 17 is attracted to the entirety of the blue Dapko due to its +2 charge. In figure 18, green or orange lines represent ion-dipole interactions. In one host, one guest system, there were more interactions per oxygen, but they're also weaker because the interatomic distance was greater. In 2 host, 1 guest systems, there were less interactions per oxygen, but they were stronger due to proximity. In order to measure ion-dipole interactions, I analyzed Hirschfeld and Voronoi charges. As a general rule, the positively charged guest received electron density from the host, or gave positive charge to the host. However, unexpectedly, the cavity atom charges, especially the inner oxygens and hydrogens, which participated in the ion-dipole interaction, actually became more negatively charged, as demonstrated in figure 20. The reason was likely to create a stronger interaction, as the central cavity needed to be more negatively charged to create a stronger ion-dipole interaction with the positive guest. The more charge transfer that occurred and the shorter the bond distance, shown in figure 19, the greater the binding energies expressed in table 4, and therefore the stronger the host-guest interaction. Enantiomeric forms of the macrocycle were due to amide bonds in the structure, Ring flipping, where chirality swaps from M to P or P to M, or any two combinations of the chirality demonstrated in figure 22, didn't occur due to the appearance of guest locking. This is a phenomenon where the dapco molecule will chain the macrocycles together and prevent conformation or chirality changes. Furthermore, ring flipping was not an issue because the energies of all these host gas systems were very similar, and therefore swapping generated systems of equivalent stability or energy. This well-evaluated 6-mer oligoamide is applicable as the study presents information on a novel host, such as how it self-assembles and binds to smaller molecules that can be used for a variety of guests, such as ions, proteins, sugars, and more. Figure 23 in the bottom left demonstrates the incorporation of the host inside cell membranes in order to serve as an artificial nanopore transport channel for different compounds. One such compound are ions. Ion channel abnormalities often cause or are symptomatic of diseases such as cystic fibrosis, Alzheimer's, myotonia, and channelopathies. For proteins, incorporation of macrocycles as amino acid transporters may occur, as figure 24 in the top right demonstrates the amino acid alanine fitting comfortably inside of the host. Finally, to combat glucose and galactose malabsorption, molecular transport of glucose and other simple sugars which fit well in the macrocycle can occur. The bottom right demonstrates a glucose molecule, highlighted in blue, fitting well inside a dimerized system composed of 2 macrocycles. This thus demonstrates its purpose as an artificial nanopore to transport different molecules, such as ions, proteins, and sugars. For future research, a study of rotoxins, or compounds that have outside groups which act as a clamp on the macrocycles, can occur, such as to create mechanically interlocked molecular architectures, or MIMAs. Notice in figure 25, for example, the bond line structure of an oxidapco with its bulky 8-carbon substituent groups attached to nitrogens, which may be combined with the current macrocycle. Further computational assessment can occur of different oligoamide macrocycles by expanding or constricting the ring size of the compound by adjusting the number of monomeric units. The macrocycle can then better fit either larger biomolecules or smaller ions. These are some of my selected references. Thank you for your time.